Hi there, and welcome to this lesson on Edexcel International A-Level for the Pure Mathematics 1. We're up to Chapter 8 and 8.1, Proof by Induction. Now, proof by induction is a powerful type of proof where you're wanting to prove a statement that is true for all of the positive integers, 1, 2, 3, 4, and so on. It's got 4 steps to it, all of which you must clearly show when you answer an exam question. Step 1. You have to prove that the statement's true if n equals 1, and this is usually easy to do. Step 2, you make an assumption. You assume that the statement is true for n equals k, some unspecified value. Now, the following step is the crucial one, and it's where understanding the logic is essential, and the clarity of your working is essential if you're to get all the marks in the exam. You have to prove that if your assumption in step 2 is correct, that the statement is also true if n equals k plus 1. So if it's true for some statement, it'll also be true for the next statement. That's what you're trying to prove. Now, if you've done that, if you've proved step 1, you've stated the assumption in step 2 and proved step 3, you have now proved that the statement is true for all values of n. Why is that? Well, step 1 proves that the statement is true for the first value, n equals 1. Steps 2 and 3 combined prove that if the statement is true for any particular value, then it's also true for the next value. If you combine these 3 steps together, we have the following chain of reasoning. The statement is true for n equals 1, we prove that, but therefore it's also true for n equals 2, because that's the effect of steps 2 and 3. We assume that it's true for one step, but we've proved that if that's the case, it is true for the next step. The statement is true for n equals 2, therefore it's also true for n equals 3. If it's true for 3, it's true for 4, true for 4, true for 5, and so on for every further value of n. What induction does is it cleverly sets up an infinite line of dominoes. You knock over the first domino, and then every domino after that also has to fall. Okay, first example. I'll let you have a go at doing this by yourself. Don't worry if you find it confusing. Induction is a little bit confusing, but have a go and then come back to me. Okay, we'll go through this together. I'd be surprised if you got there by yourself, but well done if you did. The first step is we consider n equals 1, the very first value in here, and we see if that works. Putting 1 into the left-hand side, we get the sum from r equals 1 to n of r. That is just 1. Putting 1 into the right-hand side, we substitute 1 into here. That gives us that, which is 1 as well. So 1 on the left, 1 on the right. The left equals the right-hand side. Step 1's complete. We've proved the statement is true for n equals 1. Now we move on to step 2. We assume the statement is true for n equals k, some value. All that means is we substitute n equals k into this formula. Very little has happened there. Step 2 is straightforward. Now, step 3, that's where all the action happens. We're trying to prove that n equals k plus 1 is true if the previous term, n equals k, is true. So in this question, we're trying to prove this statement is true, the statement in red, if the previous statement is true when n equals k. We start off with this type of question by rewriting the statement we're trying to prove. And we split it up into 2 parts. So the sum from r equals 1 to k plus 1, we write as the sum of r equals 1 to k, all of the terms except for the last one, and then add the last term separately. The reason why we do that is because if n equals k is true, we can write what this is. Here, we've said if n equals k is true, this is the formula we can use for it. So we substitute that in. Substituting that into there. From then on, it is just basic algebra, factorizing normally. So that's where we got to on the last page. If we factorize this, I'm taking a half k plus 1 out of both sides. And then inside the brackets, I'll have the k from here, and I'll have 2 inside the brackets, because 2 times by the half will give me the 1 that I want here. And already we've got straight to the answer. That was what we wanted to get. I left this in red because that is what we were trying to get, and this shows us succeeding. So we have finished, but the final step is just writing down the thing in a way that's acceptable, really, to show that you've finished. We need to write down three things. The wording does matter, and you should either have this wording or something very similar to it. We have shown that the statement is true for n equals 1, so we've got the process started. And we've shown the crucial bit of logic. We've shown that if the statement is true for n equals k, it's also true for n equals k plus 1. You also need to write down this last line. Something like this anyway, it needs to be similar. Therefore, by mathematical induction, the statement is true, and this is set language here, it's true for all values of n which are members of the positive integers. That's the way you'd read that little collection of symbols. True for all values of n that are members of the positive integers. Okay, example 2, have a go yourself, pause the video, come back when you're ready. Okay, we'll go through it together. So step 1, we consider n equals 1. Put 1 into the left-hand side and you will get 1. Put 1 into the right-hand side, you get all of that, tidy it up, you get 1 as well. So yes, it does work if you put 1 in both sides of the equation. Step 2, we assume that the statement is true for n equals k. This is very straightforward. We just put k into both sides and that gives us that. Step 3 is where it all happens. We're trying to prove n equals k plus 1 is true if n equals k is true itself. That means we're trying to prove this statement here, and this is the statement we're assuming is true if n equals k. Same as on the last question, we're going to split the k plus 1 into 2 bits. We split it up into all of the terms from 1 to k, and then we have to add on the last term separately. The reason for doing that is because we have a formula for r equals 1 to k that we now substitute in. So if n equals k is true, then we can substitute that formula in here. Nothing new there, and now we just tidy this up using algebra. Factorizing. This time I'm going to take a 6k plus 1 out of both of these terms. If I do that inside the brackets, I'll get k times 2k plus 1 from the left-hand side here, and 6 times k plus 1 from the right-hand side. 6, because 6 times a 6 gives me the 1 that I want here. I'm multiplying out the brackets in this big bit on the right-hand side, and then I'm collecting up the terms. That gives me a quadratic. I'll factorize the quadratic. When I do, I get this, and that is good news, because what I've got here is exactly what I was trying to get. Now, the bit that I'm trying to get, you always keep an eye on that. You know the answer with these questions. You're just trying to work out how to get there. So I knew I wanted this. I knew I wanted the 6th. That was why I took the 6th out at the beginning. So always keep half an eye on the answer, and it'll help you get there a little bit quicker. We then need to just finish things off smoothly. Nothing new there. That's what we've already done. But having done that, we've shown that the statement is true for n equals 1. We've got the process started. And we've shown the important piece of logic, that if the statement is true for n equals k, it is also true for n equals k plus 1. Therefore, by mathematical induction, the statement is true for all values of n that are positive integers. Have a go at example 3, pause the video, and then come back. Okay, a little bit different this one, and a small part of the technique feels different. Beginning's the same. Put in n equals 1 to both sides. On the left-hand side, we'll get 2 if we put 1 into there. On the right-hand side, we get that, which also simplifies to 2. So both sides simplify to 2. Therefore, we have completed step 1. The left-hand side equals the right-hand side. Step 2, we assume the statement is true for n equals k. This is easy. You just put n equals k into both sides of the statement. That gives us that. Step 3 is where the action happens. We're trying to prove that n equals k plus 1 is true if n equals k is true. That means we're trying to prove this, that's substituting k plus 1 into here. Be a little careful doing that, and substituting k plus 1 into here. Again, putting k into here. Be careful doing that. We did it on the step before. Now then, we do split this up in the same way as we did in the first 2 questions. We consider, first of all, the sum or the numbers from 1 to k. Then we need to add on the last term, the term when you have k plus 1. That gives you that. The reason why we do that is because we have a formula for the sum from 1 to k, which is here, that we now substitute in. So if n equals k is true, we can do that. And here we've substituted in the formula for n equals k into that part there. This is just rewriting the same thing again, nothing new there. In red is what we're heading towards. That's what we're trying to get. And we need to factorize and do stuff with this until eventually it looks exactly the same as that. This time, it's not always clear on these things what you need to do, to be honest. Sometimes you have to try something, see if it works. If it doesn't, try something else. We'll multiply by 2 here. So 2 times the 1 is 2. And be careful on this next bit. 2 times this term means we've got 2 times 2 to the k. Well, that's 2 to the 1 times 2 to the k. So that gives us 2 to the k plus 1 there, which is good news. We want 2 to the k plus 1, and we've got it in both terms here now. Then we've multiplied things out a little bit more. So 2 times nothing. K times this, 1 times this gives us that. K times this, 1 times this gives us that. These two terms, they're both in red because they're the same as each other and they just cancel each other out. These two terms, well, they're exactly the same. We've got 2 of them. So we've got 2 plus 2 lots of that term. Final step is factorizing that, which gives us 2 into 1 plus k times by 2 to the k plus 1. This is good news because that is exactly what we were trying to get. At that point, all we need to do, and you do have to do this, is finish the question by just explaining what you've done. So that is what we did. We have shown that the statement is true for n equals 1. We have also shown that if the statement is true for n equals k, then it is true for n equals k plus 1. Therefore, by mathematical induction, the statement is true for all values of n that are positive integers. That gets us to the end of the lesson. If you have the textbook, go to page 130 and exercise 8a. Thank you very much for listening, and cheerio.